Hello, this is your instructor again, Tom Perevsky, and it's time to start Module 9, which is on hypothesis testing. And we're going to learn in this module how to test hypotheses about means and proportions. In this first section, we're just going to introduce you to the nature of hypothesis tests. Hypothesis testing is the other major form of statistical inference besides estimation. You will recall in an earlier module, you learned a little bit about estimation, how we can estimate a parameter of a population, such as a mean or proportion. Hypothesis testing is going to have a little different flavor to it. Instead of estimating the parameter, we're going to test hypotheses about possible values for that parameter. More specifically, we're going to set up two opposing hypotheses. The first is called the null hypothesis, and is denoted by the symbol H0. The null is also sometimes called the maintained hypothesis. The reason for that is we will maintain or kind of assume that the null is true unless we get fairly sizable evidence to the contrary. The other hypothesis is called the alternative hypothesis and is denoted by the symbol HA. The alternative is also sometimes called the research hypothesis because usually what a researcher is interested in is contained in the alternative hypothesis. So in a sense, the researcher is trying to give support or show support for the alternative hypothesis. As you'll see later, what we put in the null and what we put in the alternative are mutually exclusive. You don't want the two hypotheses overlapping. You can't have the same values in the null that you have in the alternative. You might notice that hypothesis testing bears a certain similarity to our legal system. If a person is accused of a crime and taken to trial, the hypotheses in our legal system are the null is that you are not guilty, and the alternative is that you are guilty. That is, the judge and jury is supposed to maintain that you are not guilty unless they get fairly sizable evidence to the contrary. The prosecutor in the trial is very much like the researcher trying to show evidence in support of their hypothesis. The prosecutor is trying to convince the judge or jury to reject the null and conclude that the defendant is guilty. In business, hypothesis testing is sometimes used to test manufacturers' claims about a product. A manufacturer might claim that the average weight of a product is a certain amount, or that the average length of time that a product will last is a certain amount of time. These claims are usually stated as null hypotheses. That is, we will generally give the manufacturer the benefit of the doubt and put their claim as a null hypothesis, and we can often gather some data to test that hypothesis. You'll also see that whether we reject a null or do not reject a null often implies different courses of action. Rejecting the null might imply one course of action that we do not have to undertake if we don't reject the null. Let's get into more specific examples about hypotheses. Let's suppose we simply wanted to test whether the average height of men is 70 inches. First, let's go through some different possible setups for the hypotheses. Here we have a set of hypotheses where the null says the mean is greater than or equal to 70, and the alternative says the mean is less than 70 inches. In the middle here, we have a hypothesis that says the mean is less than or equal to 70 inches as opposed to the mean greater than 70. And over here on the right, we have another third possibility. Is the mean equal to 70 inches or is the mean not 70 inches? It's important to note that in all three of these hypotheses, the equality part is in the null hypothesis. It might be a less than or equal or a greater than or equal or just an equal, but we need the equals portion in the null. As it says right here, the equality portion of the equality always belongs in the null. You'll see why for that a little bit later, but I usually just like to state that we need a specific testing point. We're going to need a specific value in that null hypothesis. The alternative could say less than, greater than, or not equal to. Now, how do you know which of these sets of hypotheses to use? It all depends on what the problem is asking for and what we're looking for. And we'll get into that more in a minute. Let's take a look at these a little bit more specifically. Let's take a look at this first set of hypotheses. The null says the mean is greater than or equal to 70. The alternative says the mean is less than 70. This is sometimes called a one-sided test, and it's going to be what we call a left-tailed test, or I sometimes call it left-sided. Think of the left-tailed as because of this less than sign in the alternative. Think of that less than sign like an arrow pointing to the left. You'll actually see later on when we get into the mechanics of how to do this test, more specifically why it's called left-tailed. One-sided because the alternative hypothesis only has one range of values compared to the value that's in the null. The null basically says the mean is 70. The alternative is just interested in the possibility that it could be less than 70. Or we could have a one-sided right-tailed test. Now notice the alternative says mu is bigger than 70. Think of that greater than sign like an arrow pointing to the right, and that tells you that it's right-tailed. Again, we'll see more specifics later about exactly why it's right-tailed. Again, it's a one-sided test because only one range of values relative to the value in the null is specified in our alternative. One-sided tests are sometimes called directional. There's a particular direction implied. Finally, we can have a two-sided test. Is the mean 70 or is it not 70? Two-sided tests are also sometimes called, as I said, non-directional. No specific direction implied in the alternative hypothesis. The alternative mu is not 70 includes both the possibility that the mean exceeds 70 or that it's less 70. Again, I want to stress, in all cases, the equality portion is in the null hypothesis. I also like to point out here that the null hypothesis often indicates the way something was in the past, or maybe a standard. That's why it often is called the maintained view. The alternative hypothesis often indicates something new has happened, or that something has changed. I just want to point out one thing about one-sided tests. This hypothesis here, is the mean less than or equal to 70, or is it greater than 70? Statistically, it's no different than if I left the greater than in the null off. If I simply said, is the mean 70 or is it greater than 70? Statistically, these two tests are the same. That is, we would perform the test in the same way. What really matters in the null is that equals part. That's going to be our specific testing point. I often like to say up here that the less than sign is just sort of along for the ride. They both have the same alternative hypothesis. They both have the same research hypothesis. And the same would be true for a left-sided test. Let's do a couple of examples of hypotheses, just so you get used to writing hypotheses. Assume that in the year 2010, the average length of a phone call was 14 minutes. A statistician for the phone company believes that the average length of a call has increased in recent years. How would we write our hypotheses? Let mu equal the average length of a phone call. We're told that in 2010 that average was 14 minutes, so one of our hypotheses is going to say, is the mean 14? The statistician believes it's gone up since then. Well, that would mean that the mean exceeds 14. And then remember our rule of thumb. We need the equals part in the null hypothesis. And that also makes sense here. Like I said a minute ago, the null hypothesis is often the way something has been in the past, or a standard. So if we knew that the average length of a phone call has been 14 minutes, we'll use that as our standard in the null or maintained view. The statistician's viewpoint here is like the research hypothesis. Is the mean now greater than 14? Notice if we reject the null and conclude the alternative, we're basically saying that the average length of calls has increased since 2010. If we are unable to reject that null, then we cannot make that conclusion. We would not have sufficient evidence to conclude that the average length has increased. Let's look at a second example. A coffee vending machine is supposed to fill cups with an average of 12 ounces of coffee. If we overfill or underfill, that indicates a malfunction with the machine and calls for some kind of corrective action. Notice we really only have one hypothesis given to us here. The average should be 12. So we'll say mu equal 12 has to be one of our hypotheses. In this case, though, we're going to use a two-sided test, because if the average is either above 12 or below 12, it's going to be a problem and indicates a malfunction. So we will put both of those into the alternative hypothesis. Is the mean not 12? Again, if we reject the null and conclude the mean is not 12, it indicates that the machine is malfunctioning in some way and needs correction. And if we can't reject HO, no such action is called for. Hopefully these couple problems give you a flavor for how to set up null and alternative hypotheses, which is always the first step that you have to get by in doing hypothesis testing. Now, what are we going to do with these two hypotheses? Ultimately, we're either going to reject the null, or we cannot reject the null, or we'll say for now, accept the null hypothesis. Notice this leads, this leads to two possible errors that can be made. We make a type 1 error if we reject the null when in fact it's true. We make a type 2 error if we accept the null when in fact it's false. You might want to apply these to the court of law analogy earlier. How do we make a type 1 error in a court of law? Well, if we reject the null, and remember the null said that you were not guilty, so if we reject that and therefore we find you guilty, when in fact you were not guilty, well, we've made a type 1 error. When we send somebody to prison, or worse yet, when we execute somebody who was in fact not guilty, we've made a type 1 error. We make a type 2 error if we accept the null and therefore find you not guilty when in fact that was false and you were guilty. When we let a guilty person go free, we've made a type 2 error. And keep that court of law analogy in mind, because we'll come back to that in a few minutes in our discussion here of type 1 and type 2 error. Now, some notation. Alpha is going to stand for the probability of a type 1 error. And notice that alpha is actually a conditional probability. It's the probability of rejecting the null when in fact the null is true. Or given or if the null is true, what's the chance that we reject it? We're going to let the Greek letter beta, right here, be the probability of a type 2 error. And beta, again, is a conditional probability. If the null is false, what's the probability that we accept the null? I'd like to point out that alpha and beta are not complements. Alpha is the complement of 1 minus alpha, which you saw in an earlier module to be the level of confidence in confidence intervals. Beta is the complement of 1 minus beta. However, alpha and beta are related. Specifically, they're inversely related, which means as we lower one, the other increases, all else equal. Can you see why? If not, think back to the court of law analogy. In our court system, if you think about it, we try to minimize the chance of a type 1 error. We don't want too many not guilty people going to prison or being executed. That would be a major error to make. So we try to keep the probability of a type 1 error fairly low. How do we do that? Well, we require the prosecutor to give us evidence beyond reasonable doubt. Suppose we wanted to make type 1 error lower and lower. Well, then we will require more evidence from the prosecutor. Otherwise, we're going to find the person not guilty. You should see, though, that the more we do that, in an effort to reduce type 1 error, we're almost inevitably going to be raising the chance of type 2 error. That is, we're going to be finding a lot of people not guilty when in fact that might not be the case. If you don't see that inverse relationship, let's take an extreme case. Could we make a type 1 error 0 in a court of law? Well, yes, we could, but there's only one way to do it. Notice you can only make a type 1 error if you reject the null. That is, if you find somebody guilty. So if we never reject the null, if we find everyone not guilty, then you can't make a type 1 error. You have 0 probability of a type 1 error. But almost certainly, you've raised the probability of type 2 error. we're probably going to be finding some people not guilty who in fact were guilty, so that probability has gone up. So keep that in mind. We may come back to that later in hypothesis testing, that alpha and beta are inversely related. So we have a trade-off again. We can lower alpha, but that leads to a higher beta. Alpha gets another name. It's called the level of significance of your hypothesis test. Now, just like back in confidence intervals or estimation, where the researcher could choose the level of confidence, which was called 1 minus alpha, the researcher can generally choose the level of significance alpha for a particular test. The importance of that is if we reject the null, then the relevant error we could be making is type 1 error, but we will know what that probability is because we can choose the probability of a type 1 error. Generally, however, we're not able to assess beta, the probability of a type 2 error. Remember, type 2 error is accepting the null when in fact it's false. Let me kind of show you why we can't assess beta. Let's go back for just a moment to this hypothesis test. Is the mean 14 or is it greater than 14? A type 2 error would say we accept the null, that the mean's 14, when in fact the alternative was true. Something in the alternative is true, which means the mean is greater than 14. The problem with that is if the mean is greater than 14, well, what is it? Is it 15, 16, 14 and a half, 17? The only way we could calculate type 2 error, the probability of accepting this null when in fact this is correct, would be if we knew the actual value of the mean, which we don't. So that's what I mean by when I say we generally will not be able to assess beta. There are some advanced statistical procedures for dealing with that, but we will not be covering them in this module. Now this leads to a little bit of controversy. Sometimes people say, well, we're either going to reject the null or we accept the null, but some people don't like to use the wording accept the null. Some people, instead of saying we accept the null, prefer to say that we cannot reject the null or we fail to reject the null. You might say, what's the difference? Well, some statisticians don't like the words accept the null because if you accept the null, you could be making a type 2 error. But since we don't have control over what the level of type 2 error is, or we don't have a good handle on what the probability of that error is, some authors simply don't like to use that wording. Some authors and statisticians prefer instead to say you either reject the null or you cannot reject the null. For my purposes, it doesn't matter to me if students say you cannot reject the null or you accept the null. Just keep in mind this controversy. Even if you accept the null, that doesn't mean the null is actually true. It simply means that you didn't have enough evidence to reject it. Just like in a court of law, if you find somebody not guilty, that doesn't necessarily mean that they're actually not guilty. It might just mean that the prosecution was unable to convince you of the alternative to find them guilty. Here's a little table that just, again, kind of explains everything that can happen in a hypothesis test. Across the top here, I have what I'll call the true situation. The null is either true or the null is false, in reality, unbeknownst to us. On the left-hand side here, we have our decision. We're either going to reject the null or we cannot reject the null. That leads to 4 possible outcomes. If the null is true, and we therefore do not reject it, we've made a correct decision. Similarly down here, if the null is false, hopefully we end up rejecting it, and that would be a correct decision. The other 2 boxes are the 2 types of errors that we've just been talking about. If the null is true, but we end up rejecting it, we've made a type 1 error. If the null is false, and we do not reject it, we've made a type 2 error. Okay, now before we actually get into the mechanics of how to do a test, there are several steps to hypothesis testing. And this is one of the reasons why I think hypothesis testing is generally more difficult for students than interval estimation is. Because there's several things for you to do, and even when we get to how to do a hypothesis test on a calculator, we'll see that a calculator only helps you with certain steps and not all of them. First, you always have to determine your hypotheses. In a word problem, this means you're going to have to read the problem and from the problem decide, is it a one or two-sided test? Is it a right-tailed or left-tailed test? And so on. Specify the alpha level. That will generally be given to you in a problem. You're then going to calculate what we call the test statistic from your sample data. You're going to need that test statistic to decide, do we reject the null hypothesis or not? This leads to what I call a decision rule. We have to have some way of deciding, do we reject the null or do we not reject the null? You're going to use your alpha level to make up that decision rule. And there's going to be two different decision rules that we can use. You can use what is called the critical value approach, or it's also sometimes called the classical approach, where you're going to compare your test statistic to what we'll call a critical value and decide whether to reject the null or not. Or you can calculate something called the p-value, which we'll see is based on your test statistic, and compare it to the alpha level to determine whether or not to reject the null. And again, all of this will become clearer when we do a specific example later. Finally, you have two final steps. What's your decision? That is, do you reject the null or do you fail to reject the null? And lastly, state your conclusions in the context of the problem. That is, if you reject the null, what does that imply? What should you do? As opposed to if you do not reject the null. So there's a lot of steps for you to remember in hypothesis testing. Notice I mentioned two possible ways of doing your decision. The critical value approach, which is also called the classical or traditional approach, and the p-value approach, which is sort of the more modern approach. As we'll see, one nice thing about p-values is they can be calculated on computers and calculators, which makes it a little more convenient in this day and age. Let's give a definition to what p-values are, even though we won't actually calculate one right now until we get to a problem. The p-value is technically the probability that we get a sample result that's at least as extreme as what we did get in our sample, assuming the null hypothesis to be true. In other words, if the null is true, did we observe something in our sample that's unlikely if the null is true? So the smaller the p-value, the more likely we are to reject the null hypothesis. Our decision rule with the p-value approach specifically becomes that if the p-value is less than or equal to the level of significance alpha that we want, that's going to tell us that our test statistic is in our rejection area and we should reject the null. Whereas if the p-value is greater than alpha, we will not be able to reject the null. Again, this will become a little bit clearer when we actually start to do problems later on. So just to repeat and review the p-value approach, our decision rule will become we reject the null if the p-value is less than or equal to alpha, and we cannot reject the null if the p-value is greater than alpha. Now, that's all we're going to do in this first part, and in the next part we're actually going to get into the mechanics of how to perform a hypothesis test on a mean.